I worked at McDonald's for a couple of years.
So,
Not really.
yeah. Wait, Mr. Beaver, did they actually have pizza? You lied to me. When we were sitting. McDonald's did have pizza.
Not when I worked there.
Oh. They did, yeah.
They did, yeah, not when I worked there.
And they had lasagna too.
I never had to do lasagna. All right, we're going to talk about points of concurrency. So let's talk about vocabulary a little bit here. What do we mean when we say things are concurrent? I would say, what would I be saying? Guys, let's stop talking. What would I be saying if I said my class is concurrent with Mr. Evans' class? The same. And it's even more than the same. It's happening at the same time. Concurrent means at the same time. So when we're talking about concurrent points, if we're talking about concurrent points, guys, what would you guess we're talking about? So let's say we're talking about some lines, and we say this point is concurrent with all the lines. What would we be saying that the line happens with the lines on that point? So we have some lines, and we say these lines are concurrent at a point. Perfect. Where they all meet. So we call that a point of concurrency. So that's what we said here. Point of concurrency is the point where several lines meet. And what's the word we like to use for meet in geometry? The lines intersect. All right, so we're going to talk about today we'll talk about two special points of concurrency, and Monday we'll talk about two more special points of concurrency in triangles. And today our points of concurrency have to do with angle bisectors and perpendicular bisectors. So our first theorem, the perpendicular bisectors of the sides of a triangle and before we write the rest of this down, perpendicular bisector, what are these things doing to the sides of the triangle? Cutting them in half and to make them equal, and what's the perpendicular part tell us?
90 degrees.
Making a 90-degree angle. The perpendicular bisectors of the sides of a triangle are concurrent They all meet at one point, at a point. Equidistant. Equidistant means equal distance. Very nice. Equidistant from the vertices. The point is called the circumcenter. And we call it the circumcenter because it is the center of a circle circumscribed, drawn around the outside of a triangle. Circum just means around, and scribe means right. So let's draw a picture of what the circumcenter, how do we know if we have a circumcenter of a triangle? So here's my triangle. Just any old triangle. The perpendicular bisectors. So I'm going to kind of guesstimate at the perpendicular bisectors. So this isn't going to be necessarily perfect. Perpendicular bisectors of the sides. So there's 1, there's 2, and there's 3. And we're saying that these are all perpendicular. They all make a 90-degree angle. And they bisect the sides. So they meet at this point, P, I'll call P. And where do I want to put that? I want to put that. Point P is the circumcenter. And what the theorem tells us is that it is equidistant, point P is equidistant from the vertices of the triangle. So I'm going to draw in some lines, I'll draw dotted lines here, to the vertices. And what the theorem tells us is that all of those blue lines, all of those blue segments, are congruent. So the circumcenter is the same distance from each of the vertices of the triangle. And the circumcenter comes from the perpendicular bisectors. All right, questions on what the circumcenter is? So it's kind of interesting that all of these perpendicular bisectors meet at one point. Kind of an interesting thing. So what I want to do next is show you quickly how we construct the circumcenter. I want to circumscribe a circle around a triangle. I'm going to go through the construction fairly quickly, not necessarily for everyone to follow along. But the constructions are ones that we already know how to do. We just have to put several of them together. Yes? We're going to show that next. Okay? So I'll show you the circumscribed circle next. All right. If you can go on to, there's a website called Math Open Reference. And the Math Open Reference, you can search for constructions. And you can search this construction, and it shows you step by step how to do the construction. So I'm going to go through it kind of quickly. But you can look at it, you can look at the video, or you can search on Math Open Ref. Use that for shorthand. Math Open Ref. And see the construction. So I'm going to get a relatively small triangle. All right, so our first step, we want to make two perpendicular bisectors. The perpendicular bisectors, we're just bisecting two sides of the triangle. To bisect the side of the triangle, that's the construction. That's one of the first ones we learned, where you open up your compass more than halfway across the segment and make an arc. Bring your compass to the other side. Just want to move this in a better place. There we go. Make an arc from the other side of the segment and then connect those. Just pick any two. So there's one. I'll do another side in blue. So I'm going to do the perpendicular bisector to two sides. So I'll do this side. Open up the compass more than halfway. Make an arc. Come to the other side of the segment. Make an arc. And then I'm going to connect those two. Where those two lines meet, they meet at the circumcenter. So where those two lines cross, there's my circumcenter. The radius is from the center to any vertex. So now I'm going to get my compass. I'll do this in green. Set the point on the center of my circle, the circumcenter. Go to any vertex and draw a circle. If I do my construction perfectly, pretty close, it will go through each vertex of the triangle, and it should just touch each vertex. So it's a little off there, but I made my dot kind of big so it could end up moving around a little bit. So if we do our construction perfectly, that green circle would go exactly around the triangle. The triangle will touch the circle just at the vertices. And that's called that's the circle that's circumscribed about the triangle. The triangle is supposed to fit exactly inside if we do our construction very carefully. And we draw the circle. So this point is the circumcenter, and the circle is our circumscribed circle. And we found that by constructing perpendicular bisectors to two sides of our triangle. I mean, I could construct the perpendicular bisector to the third side, and it should go right through the same point. Questions there? Okay. The circumcenter can be inside the triangle. So if my triangle looks like so, my circumcenter is going to be inside. And these are the perpendicular bisectors. I know they're not perfect, but so our circumcenter can be inside the triangle. It can be on the triangle. If we have a right triangle, our circumcenter turns out to be on the triangle. So if I draw two perpendicular bisectors here, or outside the triangle. If we have an oblique triangle. Not an oblique, obtuse. Oblique just means no right angles, none of the angles are the same. So this would be an oblique triangle. Obtuse, one of the angles is bigger than 90 degrees. So our circumcenter here would be outside the triangle. So it can be any one of those three places. And if I drew the circle would go exactly around that triangle. It's kind of cool when you do it. It's really nice when you do it with an obtuse triangle. It looks really nice. So it can be any of those three places. All right, questions there? All right, we have one more point of concurrency we need to talk about today. The angle bisectors. The angle bisectors of a triangle, what are the angle bisectors of a triangle doing? Cutting what in half? The angles. So we're bisecting all three of the angles. The angle bisectors of a triangle are concurrent, at a point, so they all meet at a point, that are equidistant from the sides of the triangle, or that is, the point is, side is, this point is called the incenter. So our angle bisectors meet at a point in the triangle. That point's the same distance from all of the sides of the triangle. Is called the incenter. And it is the center of the circle inscribed in the triangle. So instead of the circle going around the triangle and touching each vertex, it's inside the triangle and touches each side. So let's draw a picture of what the incenter, how we tell if we have an incenter. So we're going to have the angle bisectors. So I'm just kind of guesstimating on the angle bisectors here. And we know it's the angle bisectors because all of those angles are split in half. So just like we did on our opener, all those angles are split in half. That's an angle bisector. Angle bisectors. And this, we call this point P. P is the incenter. And the theorem tells us that it's equidistant from the sides. Now yesterday we decided, how do we measure the distance to something? If I want to measure the distance to the back wall, what do I have to make sure I do? Make it perpendicular to the wall. I have to make it a 90-degree angle to the wall. So to measure the distance from each of the sides from our incenter, I have to make sure that I go perpendicular to each of the sides. So all of those are perpendicular. And what the theorem tells us is all of those blue segments are congruent. We're on the angle bisectors, so this point is the same distance from each side of the angles in pairs. So the incenter is the same distance from all the sides of the triangle. All right, questions? All right, let's look at our construction for the incenter. Again, you can find this on Math Open Reference. I want to make this triangle a little bigger. It's a little easier with the incenter to have a little bigger triangle. All right, so our first step, we're going to construct two angle bisectors. The angle bisectors, that's one of the first constructions we learned. That's where we make an arc through our angle. Then we move our compass. Make sure our compass is open more than halfway across. Make an arc on that side. Move our compass, make an arc on the other side. And then go from the vertex through that where we made the little cross. And I'm going to extend it because I want to find where this intersects with another angle bisector. So I'll do another one in blue. So I'm going to go over here, I'll do that side. I can pick any two sides. Make an arc, measure more than halfway across. Make one arc. Another one. This automatically makes a circle sometimes. And then I'm going to connect my vertex through that little X. And where those meet is the incenter. Yes? The which one now? This one?
No,
the one that made a circle. So what I did was I had my compass. I had it setting here. I just made sure it was open more than halfway across the angle. So that's where that arc came from. And then I just took the compass. I didn't move it. I just moved the point over to the other side of where the arc crosses the angle, and then made an arc there. Okay. All right. So that's the incenter. Now we need to find the perpendicular distance to one side. So we need to make sure we're going at a 90-degree angle. So that's our smiley face construction. So smiley face to one side. So I'll do it down here. We'll do that in red. So this one takes a little more work. So the smiley face construction, I just have to go, so make sure I'm past the segment. Make my smiley face. And then I'm going to bisect the smile. That's the same construction I did last time. Make sure the compass is open more than halfway across the smile. Make an arc down here because I'm going to go through that point. Move the compass to the other side. Make an arc there. And then connect those. So there's the bisector, perpendicular bisector. The radius is from the center to the side. So now I can make my inscribed circle. I'll do that in, I need to pick a new color. How about a purple? So I go from the center to that side where I made my smiley face. And this one's a little harder to do really well. If I do it perfectly, it should touch. Just missed there and I just missed there. Darn. It should perfectly touch all three sides of the triangle. But if we don't, so we have all of these that we have to do perfectly correctly. But we got pretty close there. So the purple triangle is the inscribed circle. If we do it perfectly, it touches each of the three sides.
Yes.
So incenter means the circle ends up inside the triangle. Circumcenter means the circle ends up around the triangle. Circum means around, like we circumnavigate the globe, like Magellan circumnavigated the globe, means go around. Incenter just means it's inside. Okay? That's the difference. All right. Now let's take a look at a couple of quick examples of the types of problems you might see on your homework with these things. One other thing I need to say, the incenter is always inside. So the incenter can't be anywhere else than inside the triangle. The circumcenter can be in, on, or outside. Incenter is always inside. All right, let's look at a triangle. Here's my drawing for this. On all of these, I suggest that you first figure out what type of thing you're talking about before you start to solve the problem. So you know that you're using the right procedure. Yes? You'll be given lines or some way to figure out something about you'll have information that has those on there. All right. So first off, let's look at this triangle. And with the information given to us, what kind of special point is point G? So these are the lines that I've drawn there from the vertices of the triangle. These are angle bisectors. Angle bisectors give us the circumcenter or incenter? Incenter. G is the incenter. The incenter is the same distance from what? The vertices or the sides? Sides. All right, so now I'm going to draw some more lines in here. So these would also be in your problem. So before I even write anything up here, I'll call this point B and this point F. What do we know about BG and GF? They're perpendicular to the side, so that tells us the distance to this side of the triangle, the distance to that side of the triangle. So they're congruent. So BG, and I'm just writing out how we would think about this problem, not necessarily how we'd have to solve it. All right, so here's what the problem gives us. Here we'd have this picture, and the problem would say BG equals 8x minus 7. GF equals 5x plus 8. Find x. So what do we do? I'm going to change it. Find BG. So what are we going to do? Set them equal to each other. We figured out before we even looked at what they asked us to do that those two have to be the same length because the point G is the incenter. So we say 8x minus 7 equals 5x plus 8. And now we're set. We like this kind of problem, right? (3x minus 7 equals 8). So I get 3x equals 8 plus 7 is 15. And x equals 5. Are we done? No? Problem says find BG. So we need to do 8x, 8 times 5 minus 7. 8 times 5 is 40 minus 7 is 33. So BG is 33. Figured out that was the incenter. Use that to help us solve our problem. How would we know if we were just given this drawing and they didn't say this? How would we know that these are not the perpendicular bisectors of the sides? They're perpendicular, right? Yeah. So how would we know that this is not the circumcenter if we're given this picture? I'm going to say these are not the perpendicular bisectors. How do we know that they're not? What do we have to know about these two segments for this to be the bisector? They have to be congruent. We do not know that they're congruent, so those can't be the perpendicular bisectors. So we have to use the information about the angles. All right, one last example. Sometimes you'll be given a problem that has to do with coordinates. Find the circumcenter. So here are my axes. There's the y-axis, and there's the x-axis, and I'm going to draw a triangle on here. 1, 2, 3, 4, and 1, 2, 4, 5, 6, 7. And this point is 4, 0. And this point is 4, 0, 0, 4. 8, 0, and this point is 0, 0. All right, what do I need to draw? What do I need to construct? What do I need to do to find the circumcenter? We need some kind of bisector. What is it? Angle bisector for circumcenter? Perpendicular bisector. All right, let's bisect a couple of sides. What's the middle of this side? Go up 2. So that point is 0, 2. If I go perpendicular to this side, which direction do I need to go? Right. To the right, straight across, right? Parallel to the x-axis. So I'm just going to draw that line straight over to the right. Right along that grid line, right? What's the middle of this side? 4, 0, right? 1, 2, 3, 4. That point right there. And what direction do I go to go perpendicular to that side? What is it? Upward, straight up, right? Those cross right there. What are the coordinates of that point? Go over 4, up 2. And notice it's right on the hypotenuse of the triangle. So we had a right triangle, so it's on the triangle. Questions there? Okay. Homework. Page. Thankfully, we don't have to do things that long very often. Page 05. Find it 8 through 18 even. And also part of your homework is the 5.3 dynamic activity. So on power geometry, it'll be in your to-do list, just like we did in class yesterday. Click the 5.3 thing and just do the dynamic activity. All right, let me